Welcome aboard. This will start our lecture series for Physics 201 using the Ch1a book. So Chapter 1, Introduction, Measurement, and Estimating. First, we'll start by introducing the nature of science and what models, theories, and law are, just kind of getting some of the semantics out of the way. Then we'll talk briefly about uncertainty and significant figures. The really important part of this chapter is going to be the SI system of units that we'll be using. If you've taken other science classes, you're already somewhat familiar with it. We'll get some practice with converting units, and we'll talk briefly about dimensions. So what do we do as scientists? Well, we're always asking the age-old question, why? So we first make an observation, and then we think, well, why does that happen? What we do then is we create a theory. This theory should be able to explain the observations that we're making. From this theory, we should also be able to make predictions of what will happen in other situations. Then we go on and we make our observations. These observations tell us if our prediction was accurate or if our theory was accurate. If it was, then we keep on going. If not, then we go back and we make more observations, we make more theories, and we make more observations. So how do we know if a new theory is right? How does it get accepted by the scientific community? Well, first of all, the predictions are going to agree better with data than a previous theory. Also, it's going to explain a larger range of phenomena. So, for example, if we think about the solar system, originally people had the Earth right here at the center of the solar system, and saying, that the sun went around the Earth and all the other planets also went around the Earth. That makes some sense. I mean, we see the sun rise in the east, come down in the west, and we see that pretty much every day. And we also see the planets traverse our sky. However, if you really look at the position of planets over time, you plot them in the sky. For example, Mars would do a little blip like that over the course of a year. And so a fellow by the name of Copernicus came up with a theory that the sun is going to be at the center of the universe, and all the planets go around the Earth, or go around the sun. The sun will still rise in the east, go down in the west, but that also explained this observation that he made of Mars. So eventually, at some point, the new theory became accepted, and now we know a lot more about the universe, and we can make more predictions from that. So how does physics relate to all these other scientific fields? This is kind of my heuristic view of the universe. I think of it as kind of a triangle, with logic being the base of the triangle, and mathematics using logic to create expressions. However, everything down here, I think of kind of the abstract universe. We have these strange symbols, and it doesn't really connect to our universe very well. Physics uses math. We'll be doing a lot of math in this class. It's kind of like the language of science, the language of physics, if you will. So here we have physics, and all of the other sciences, they build off of physics. They use physics. For example, chemistry, the behavior of atoms, some of the bonds that are behind that, that comes back to physics. The same with biology, astronomy, geology, zoology. They all have applications of physics, if you will. Engineering and technology has a basis in physics. Of course, it's vital that we have good communication between all of the fields of sciences. They have their basis in physics, but really physics can also learn a lot from the other sciences and essentially be able to solve a lot of their puzzles. Communication, of course, is always going to be important. If you think about communication between physicists, architects, and engineers, if you can have a building, you can have a structure that could last 1,000 years. There was good communication between the people that designed the bridge and the people that built the bridge. Or you could have a structure that might last only 10 years. Another example is, I used to work at NASA, and about 10 years ago we crashed a probe into Mars. Turns out the reason was poor communication. It was essentially one group was using the SI system of units, and the other group of people was using the English system of units, and so it was a unit conversion problem. So poor communication led us to crash a several $1 million instrument into Mars. So let's talk briefly now about the scientific method, which is really going to be about how we go about solving problems, so problem solving. We start, and we do this in our everyday life, whether you realize it or not. First, we come up with a puzzle that we need to solve or an observation. For example, we might say, my car is not starting. So what we do is we make a hypothesis. Take a look at my car. It could be a whole lot of things. My hypothesis is my car is not starting because it is in drive instead of park. Make a prediction. I'm going to put my car into park and see if it'll start. Test my theory. Try to start my car. Theory. A car is not going to start in drive. It has to be in park to start. If that wasn't necessarily the solution to the problem, then we go back up to our puzzle and say, okay, I have a problem. My car won't start. Make a hypothesis. Maybe my battery is dead. Make a prediction. If I connect it to another car using some jumper cables, it'll start. Test that hypothesis. Theory. Car started. I had a dead battery. So this thing called the scientific method is something that we use in our everyday life. Now, physics, much like all the other sciences, we use that scientific method. We're experimenting with our environment. We're looking to understand kind of the broad nature of the universe around us, kind of how things physically behave. Once we've gone through the scientific method, we have some physical theories that are going to relate how objects are going to behave with one another. Once we have a physical theory, then we're going to test it and test it and test it time and time again using the scientific method, making sure that it can explain the broad nature of the universe. Once we have a theory that's very, very, very well established, we're going to call that a physical law or a principle. Some physical laws that we'll be talking about in the next chapter are going to be Newton's laws, which are essentially going to describe how objects accelerate, how objects move. So now let's get into the meat of things. Let's talk about making measurements and the uncertainty that's involved with that. Let's take a look at trying to measure this 2x4 right here. Now we know that this 2x4 is going to be 3.5 inches, but let's talk about it in using the metric system here. You can kind of see the length of this 2x4 is going to be, the end of it's going to be right about there. I might say that the width of this guy is going to be, let's just say roughly 8.8 centimeters. Now, there's some difficulty in me trying to read this. It could be 8.9 centimeters. It could be 8.8 centimeters. So there's some uncertainty in any measurement that you make. We can write this uncertainty, here we're talking about the width of that 2x4, using a plus minus sign. We say the width of this 2x4 is going to be 8.8 centimeters plus, give or take, about maybe 1/10 of a centimeter. That's probably about as good as I can read the ruler scale. We can talk about percentage uncertainty. That's going to be the uncertainty here on the top divided by the measurement multiplied by 100. And we're going to get a percent uncertainty about 1%. I know the width of that 2x4 to within a percent. Now, this uncertainty starts to come into play when we start talking about significant figures, and I'll warn you that I'm not a huge stickler for significant figures when it comes to your calculations, but I do need to talk about them just briefly. Essentially, the number of significant figures tells us how precise we know a measurement. If we take a look at this measurement right here, 23.21 centimeters, that says, okay, I know this measurement all the way out to the 100th place here. How I count significant figures is essentially how many digits do I have, and the trick starts to come into play when we start talking about zeros. Starting off with this one, it's going to have 1, 2, 3, 4 significant figures. Now, zeros are a special animal. They are essentially just placeholders, and they're pushing our number out to the level of precision that we have. So zeros that are before the decimal place are not going to count as significant. They're really just kind of moving the other numbers around the decimal place. So if we look at 0.0062, those two zeros are not going to count as significant figures. The only two values that are going to count are going to be these two values right here, so we're going to have two significant figures. Zeros that are in between other non-zero objects, suppose for example I wrote 806, that's going to have that zero is going to count as a significant figure because it's not pushing around the 8 or the 6, it's really in between these two guys. So this one would have 1, 2, 3 significant figures. Trailing zeros, they can be kind of ambiguous. If you look at 80 kilometers, the way I would read that is I would read that as, this last place here it's going to be, plus or minus 1 kilometer, and so I'm going to actually have two significant figures here. If we wanted to write it as 3, we would write it as 80.0 kilometers. This trailing zero is now going to count as a significant figure because it's saying, I know the precision of my measurement all the way out to the 10th place. So this is going to have 1, 2, and then 3 significant figures if we write it that way. Now we start to run into significant figures when we're adding, subtracting, multiplying, or dividing. And essentially when we're multiplying or dividing, the result should have as many significant figures as the least significant number that you are multiplying. For example, 11.3, that's going to have 1, 2, 3 significant figures. 6.8 is going to have 2 significant figures. So if you multiply them together, you're going to get 76.84 centimeters. We need to cut this down to 2 significant figures. That's the number with the fewest significant figures. So we're going to write that as 77 centimeters. Just a disclaimer, I am not a stickler for significant figures so much, so if you wrote 76.84 or 76.8, that is perfectly okay with me. If you rounded it up and you wrote, say, 80, that's starting to push the limit. So including more decimal places is perfectly fine for me. If you're adding or subtracting, it's going to be no more accurate than the least accurate number used. For example, if you have 11.3 and you say, I'm going to subtract off 6 from that, then that's going to be 5.3. If we wanted to be totally precise, we would have to round that down to the least accurate number used, which is going to be 6, so we'd say that should be 5.